On behalf of the SCSTE, I would like to welcome all viewers and especially our dear students. And today I'll be continuing on the chapter of real numbers, which I left out on the last online class. So let's begin. Class, we've talked about Euclid's lemma, and today I'll be starting from Euclid's division algorithm. So, last class we've talked about Euclid's lemma. Now in this class we talk about Euclid's division algorithm and how to find the SCF of two given positive integers. So first of all, this word algorithm is a series of well-defined steps in order to solve a problem. Alright. Now we have to remember first of all that Euclid's division algorithm usually involves 3 steps. Alright, sometimes it involves only 2 depending on the given positive integers. So step 1, we have to apply Euclid's lemma to the given 2 positive integers. Step 1, we just apply Euclid's lemma to, suppose those 2 given positive integers we denote by a and B, where a is greater than b. Alright. Then according to Euclid's lemma, there must exist 2 whole numbers, and we denote those whole numbers by q and r. So according to Euclid's lemma, there exists whole numbers q and r such that we can write a in this form: a is equal to bq plus r, where r is greater than or equal to 0 but strictly less than b. This is according to Euclid's lemma. Alright, so step 2 is to check whether the remainder is 0 or not. Alright, so first of all, if the remainder is 0, that means we've already got our required HCF. Then HCF of a and b, this is how we denote HCF of a and b. HCF of a and b is b. Alright, but if the remainder is not 0, then if r not equal to 0, then apply Euclid's lemma again, but not to a and b again, but now we apply Euclid's lemma to b and r. Alright, so now we'll have to move on to the third step, which is step 3. And in step 3, we just have to repeat the process until we get the remainder to be 0. Then the last divisor at that stage will be the required HCF. So in step 3, we just repeat step 2 till r is equal to 0. Then the last divisor, or the divisor at that stage, alright, and the last divisor at that stage is the required HCF. Alright, so let me explain to you this algorithm properly by solving a problem from exercise 1. So we solve only one problem from exercise 1A, which is number 1, exercise 1A number 1, part 4. And the question says, the question tells us that we have to find the HCF using Nucleus Division algorithm, alright, of the given pair of numbers. So the given numbers in question number 1, part 4 are 100 and 190. So according to Nucleus Division algorithm, first of all, we use step 1, alright. Step 1 is to apply Euclid's lemma to these two given positive integers, alright. So according to Euclid's lemma, we denote A to be the greater number. So here we clearly see that 190 is greater than 100, so A is 190. And then B will be 100. So, according to Euclid's lemma, we can find two positive or two whole numbers given are such that we can write A in this form. So let us divide 190 by 100. So first of all you go with 1, and then the remainder left out is 90. So we've got our required two whole numbers, which are 1 and 90. So that means we can write 190 in this form, 100 into 1 plus 90. Then we move on to step 2. Step 2 is we have to check whether the remainder is 0 or not. Here we clearly see that the remainder is 90, so it's not 0. That means we have to apply Euclid's lemma again. Now we apply Euclid's lemma to B and R. Here B is 100 and R is 90. Alright, so we move on to step 2. So step 2 says to apply Euclid's lemma to B and R if the remainder is non-zero. So we'll apply Euclid's lemma again. So B in this case is 100 and R is 90. So let us divide B by R, which is 90. So you go first by 1, 90 into 1 you get 90, and then the remainder will turn out to be 10. Alright, so according to Euclid's lemma, we can write this dividend, which is 100, in this form. 100 is equal to 90 into 1 plus R. Here again we see that the remainder is still not 0, so we have to apply Euclid's lemma again to B and R. But here in this case, B is 90 and R is 10. Alright, so let me just denote that. But remember, these B and R are different from the first one. So we apply Euclid's lemma again. So let us divide this B by R. So you go with 9, you get 90. Here we see that the remainder is 0. So 90 can be written in this form, 10 into 9 plus 0. So now we get the remainder to be 0. Then according to step 3, that last divisor, alright, is our required SCF. And here we clearly see that our last divisor is 10. So therefore the required SCF, let me just write therefore the SCF of the two given positive integers, and in this case it's 100 and 190 is 10, because 10 is the last divisor. Alright, so now let us move on to the next topic, which we'll talk about fundamental theorem of arithmetic. Now we'll talk about fundamental theorem of arithmetic. This theorem states that every composite integer can be expressed or factorized as a product of its prime factors, and that factorization or expression is unique apart from the order in which the prime factors occurs. Alright, so let me just write down what I just said. Every composite, even though I write down number, but here in this case we're talking about integers. Alright, so every composite number can be expressed as a product of its prime factors and this expression or factorization is unique apart from the order which the prime factors occurs. Alright, so let me give you an example to understand the theorem properly. So if you take any composite number, or in this case we're talking about integers, so let's take randomly 6. 6 is a composite number. Why? Because 6 has at least 3 factors, right? And we know that the factors of 6 are 1, 2, 3 and 6 itself. Since 6 has at least 3 factors, so that means 6 is a composite number, because the definition of composite number is a number which has at least 3 factors. Alright, it may have more than 3, but the minimum condition should be 3. Alright, so we clearly see that 6 has 4 factors, but among these factors only 2 and 3 are prime factors, because these are also prime numbers. Prime factors are factors, but they should be also prime numbers. Alright, so that means according to this theorem, this composite number 6, we should be able to write it as a product of its prime factors, which means as a product of 2 and 3. And we clearly know that 6 can be written as 2 into 3. Alright, and the second part of this theorem, it says that this expression is unique apart from its order. What do we mean by this expression is unique? It means that we cannot find any more prime factors of 6 such that we can write 6 as a product of those prime factors. Alright, we clearly know that 2 and 3 are the only prime factors of 6. There are no other prime factors of 6, so that we can write 6 as those prime factors. That is why this expression is unique. Right? So the order doesn't matter, alright? Because 6 can be written as 2 into 3, or 6 can be written as 3 into 2, but the order doesn't matter. Alright? So now let us solve one problem from exercise 1C, where we have to apply this theorem. Alright? So from exercise 1C, question number 1, part 1, the question tells us that we have to find the prime factorization of 96. Alright? So, first of all, prime factorization is a method where we split or we break down a given number, alright, or when we factorize a given number as a product of its prime factors. Alright? So, we have to find the prime factorization of 96. So first of all, we draw a vertical line, and then we keep on drawing horizontal lines depending on the quotient. Alright? If the last quotient you get to be 1, then we stop the method. Alright? So first of all, we have to find the prime factors. So we do not divide 96 by any other number which is not a prime factor. Alright? Because 96 is divisible by 1, but we don't go by 1 because 1 is not a prime number. Alright? And also it should also be a factor. Alright? So we do not divide 96 by 4, because 4, even though it can divide 96, but still 4 is not a prime factor. Alright? So we start with the least prime, which is 2. 2 can still divide 96, so we go by 48, and then we keep on dividing by the same prime depending on whether that prime can still divide the quotient or not. Alright? So we clearly see that 2 can still divide 48, so we keep on dividing with 2, so we get 24. Now we clearly see that 2 can still divide 24, 2 can still divide 12, 2 can still divide 6, but now we see that 2 cannot divide 3. Alright, so we move on to the next prime number, which is 3. So we have the quotient to be 1, so we stop this method at this stop. Alright, and so we get 96 to be a product of how many terms? 1, 2, 3, 4, 5, So we can just write 2 to the power 5 into 3. So we clearly see that this number satisfies this theorem, right? Because 96 is a composite number, and we clearly see that 96 can be written as a product of its prime, alright? And the order doesn't matter, you can write in this form or in this form, alright? So now let's move on to the next topic. Now we'll do two theorems, and from those theorems we'll try to solve some exercises from the last exercise, alright? So the first theorem is that x be a rational number which has a terminating decimal expansion then x can be written or expressed in the form a by b, where a comma b are co-prime and the prime factorization of b is of the form 2 to the power m into 5 to the power n, where m and n are non-negative integers, non-negative integers or whole numbers, alright? So, according to this theorem, if we have a rational number which has a terminating decimal expansion, then we can express or we can write that rational number in this form. In the form a by b, where a comma b are co-prime. Co-prime means the SCF of a and b is 1. Alright? So, and the prime factorization of b must be of this form, 2 to the power m into 5 to the power n, where m comma n are non-negative integers. Alright? So, let me just tell you the converse of this theorem. The converse of this theorem is also true, which means that if we have a rational number which is of this form, a by b, where a comma b are co-prime and the prime factorization of b is of the form 2 to the power m into 5 to the power n, where m comma n are non-negative integers, then that rational number which is of this form will have a terminating decimal expansion. That's the converse part of this theorem. Alright, so now let me do the second theorem. So the second theorem says that if x is a rational number of the form a by b, where a comma b are co-prime and the prime factorization of b is not of the form where m and n are non-negative integers then x has a non-terminating but repeating decimal expansion. So this theorem says that if we have a rational number of this form, where a comma b are co-prime and the prime factorization of b is not of the form 2 to the power m to 5 to the power n, then this rational number will have a non-terminating but repeating decimal expansion. Because we have to remember that there are two definitions of rational numbers. The first definition is that rational numbers are those numbers which is of the form p by q, where p and q are integers and q is non-zero. And the other definition is that those numbers which have a terminating or non-terminating but repeating decimal expansion, those are also rational numbers. Alright, so this theorem helps us to classify rational numbers. So now let me solve exercise 1e. Question number 3. 1. It's given to be 125 by 44. Alright. The question says that without performing the long division method, we have to say whether this rational number has a terminating decimal expansion or non-terminating but repeating decimal expansion. Alright. So first of all, we have to use those two theorems which we have done. Alright. So first of all, the first theorem says that these two, this numerator and denominator, they must be co-prime. So we clearly see that 125 and 44 are co-prime, because if you find the SCF of 125 and 44, you get the SCF to be 1. So these numbers are co-prime. So we've checked that condition first. And then the prime factorization of b must be of the form 2 to the power m into 5 to the power n, for it to be a terminating decimal expansion. But we clearly see that here 44 is 2 into 2 into 11. It is not of this form, 2 to the power m into 5 to the power n. It's not of this form. So that means, according to theorem 2, this rational number will have a non-terminating but repeating decimal expansion. Alright, so let's look at the second part. It's given to be 23 by 8. This rational number given to us is 23 by 8. So here also we clearly see that these numbers are co-prime, because the SCF of 23 and 8 will get to be 1. Alright, so these numbers are co-prime. So let us look at the denominator. We clearly see that the denominator is 8 is equal to 2 to the power 3. We clearly see that this is of the form 2 to the power m. But we cannot find 5, right? But we can introduce by ourselves, because we can write it as 5 to the power 0. Because 5 to the power 0 is 1. So that means you get back to cube. So this is correct. Alright, to write in this form. So we clearly see that 8 can be written in this form, 2 to the power m into 5 to the power n. Here m is 3 and n is 0. So that means, according to theorem 1, this rational number will have a terminating decimal expansion. Alright, so we've come to the end of this chapter, and I hope that you have gained a lot of benefit from this online class, and in the next online class we'll be doing a new chapter. Thank you.